Right, so I'm going to give a general overview of something that's called optimal dynamic treatment regimes, or variants of that. Not particularly related to the paper that will be read this evening. And then the main man, Lheure, will talk about more specific aspects of this problem that are closely involved in what he's going to talk about this evening. Okay, so I'll just introduce the general area. I'll say something about two of the several methods there are for estimating the parameters of these models. And I'll touch on some of the assumptions that are generally made for causal inference. Okay, so optimal dynamic treatment. We'll start with some notation. I've tried to make my notation similar to what is used in the paper, but there will be variance at times. This grew in the area of personalized medicine, where the objective is to treat somebody in the optimal way for that person, given what you know about that person, rather than saying this treatment policy is appropriate for everyone, let's tailor the treatment to the individual. Sometimes you've got to learn about the individual over time, so it's a dynamic process. You start by knowing nothing about the person, and then as information accrues, you know more about them and you tailor the treatment to them. It's optimal. You want the best possible treatment for that person. So we assume that there are a number of time points. T is 1, 2, and so on in some sort of set. Often, if you look in the literature, that's restricted to just 2, maybe 3. But in principle, it could be a larger number. Then at each time point, let's suppose it's a clinic visit, a patient turns up to the clinic, and the clinician, the doctor, looks at them and measures something on them. Okay, they can measure their state of health, whether it's blood pressure or it's a questionnaire for quality of life or something like that, and they've got some information about them. They know the state of the patient at time t, and that's called S. So S is the state of the individual. And then a certain action is chosen. So A for action or treatment or whatever it happens to be. The clinician chooses what to do next. Do I change the treatment for the patient? Do I change the dose of the drug for the patient? Do I leave things the same? Do I tell the patient to come back at an earlier time point than we might have expected? Or do I tell them to go away? We never want to see you again. They make some sort of a decision. Again, in the literature, often the actions are restricted to just 2, a binary action, treat or not treat, treatment A, treatment B, something like that. But again, in principle, there can be a wider class of actions. And then the aim is to optimize some sort of outcome. And in the paper, that's called Y, Y1, Y2 over time. And that might be the state of the patient at the next visit. Or it might be how long the patient will live, or something else. Or it might be a function of an outcome, some function of the state, and so on. These outcomes might accrue over time. So every time you see the patient, you might get an outcome Y, such as their blood pressure being in a certain band. Or you might wait until after a sequence of treatments and have some final outcomes. So going away from medicine, you might be training somebody to take an examination. And they come with a certain amount of knowledge, and you give them some tutoring, and then they come again, and you tutor them again. And Y is the score on the final examination. Okay, so the outcomes can accrue, or they can be fixed in time. Now, here's the simplest possible example that I could think of. Everybody has the same initial state, S1. So that's the same for everybody. And then there's a binary treatment. A1 is 0 or 1. The patient goes away and comes back again, and there's again a binary state. S2 is, that thing's not working, because it hasn't got a laser, never mind. S2 is 0 or 1. Patient goes away, after seeing S2, the clinician decides again between a binary treatment, A2, 0 or 1, and then we measure an outcome, A. And I put some numbers on there that I'll come back to later to reflect what might have happened in the observational data we are going to use to determine the optimal actions. So at the first decision point, 1 minus p is 0.5 and p is 0.5. That means in my data, half of the people got A1 is 0, half of the people got A1 is 1. And then when A1 is 0, at the top there, 1 minus P0 is 0.2, P0 is 0.8. That means S1 is 1 for 80% of the people who had A1 is 0, and S2 is 0 for the other 20%. Now we assume that we, or the clinicians, or someone, is in control of choosing A, so we can choose the probability that A is 0 or A is 1, or somebody did. But the states are determined by nature. They're random variables by God, whoever you like. Somebody else determines S. We can't control that, and in the future we'll have no control of it. It's a random variable. So what's the optimal treatment allocation policy in this simple example? I'll come back to that shortly. Now we'll go to the other end of the scale, an example that's as complicated as it gets in this type of application area, and this is anticoagulation for people who are at risk of thrombosis. So if people have had a heart attack or a stroke, if they get a blood clot, if they're at risk of a blood clot, this can go to their brain or their heart and cause damage. So they're given drugs, anticoagulants, usually something called warfarin, to slow down the time in which it takes for their blood to clot. A problem is that the optimal amount of drug depends, a lot between patients. Some people need a large dose, some people need a low dose, and also it varies over time within a patient according to their particular lifestyle. If they've had a lot of cabbage, they'll need less warfarin. If they've had a lot of alcohol, they'll need a different amount of warfarin. If they've done some exercise, they'll need a different amount of warfarin, and so on. So these are data that we received recently. It's one patient from a larger group, and the top shows how the dose was changed for this patient in response to a measurement of blood clotting speed. And the measurement is something called the INR, which is the International Normalized Ratio, and it's basically the ratio between how long it takes the patient's blood to clot and how long it takes a control patient's blood to clot. So if you're an ordinary patient, that would be 1. But for people at risk of thrombosis, the clinicians try and maintain this INR in the range 2 to 3. So that's the band that is in that lower plot there. So the outcome in this case is whether or not the INR is in range. The state is the actual INR at the clinic visit number T, and the action is the dose between that visit and the next visit. And you can see that it's very variable. So to begin with, the patient's INR was too low, and therefore the clinicians increased the dose. That will increase the INR. They've got the patient within range, and then it started to wobble about, so they decrease the dose and then back up again, and this is a dynamic strategy. Okay? This is a fairly typical patient. Things happen, things make the patient very variable, so the dose needs to react to that. Sometimes the doctors overreact, so towards the end, that trough around about 2011, they decreased the dose, but they decreased it too far, and it had to go back up again. Now what would be good would be to have some sort of a rule, some sort of a objectively derived rule which guides the doctors as to what dose they should give. In fact, there are some rules out there already. Can we do better than that? This is a fairly typical patient. Here's a different patient. This is fairly rare. This is a patient who started off with an unknown optimal dose, and the INR wobbled around, and the dose wobbled around, and eventually they got the patient stable. So they found the right dose for this patient, and they left it alone, and the patient stayed in range for a couple of years. And that's pretty much the ideal scenario where you find the right dose for that patient. Sometimes you get the opposite effect. So here's a third patient where everything was okay, and everybody was happy. The dose was fairly constant, the INR was fairly much in range, and then something went wrong. And it just got very volatile, and so the INR went up, the dose went up, the INR went down, the dose went down, and so on. The patient, for some reason, went out of control. So those are examples of cases where we need where we would like to find rules that are optimal, that are dynamic for allocating treatments. A little bit of notation. So H is the history. That's everything that you know when the patient presents at visit T. So you know all the previous states, and you know all the previous actions. You know the current state, but you don't know the current action yet. You haven't decided that. And you know the outcomes in the past. And what we want to find is a rule that says, given this vector H, this is the best decision. And I'll call that D. So D of H of T is a rule. It's not an action. It's a rule that says, if this, then do that, which allows us to choose the best action, best treatment for the patient, given what we know at that point. What's slightly unusual in the paper that we will have tonight is that instead of having a deterministic rule, the authors are proposing a stochastic rule. So they are suggesting, in a slightly different context, that instead of knowing precisely what decision we're going to take, we'll draw from a distribution. And that distribution is based on the posterior, given the parameters and the model that we're playing with. I'd never come across it before, but it's called Thompson sampling, where you choose a treatment according to the probability that it's the best. It's a random allocation. Sometimes you see the word regime when you read about this, and a regime just means a sequence of rules. So a rule is what you do at one time point. A regime is a sequence of rules over time points. Okay, so what do we want to optimize? As mentioned previously, we might want to optimize a final value y, whether or not I pass an examination, whether I live for 5 years. I might have some utility on this, some sort of quality adjusted amount of life. I might have the average of a sequence of outcomes over a future window, the average of the next 5 visits, or a discounted average, and that again is what will be used in the paper tonight. So the 1, 2, 3, fourth of those bullet points says take each outcome, y of t, find some sort of utility based on that. So if the outcome is in range or out of range, the utility may be 1 if you're in range and 0 if you're out, or it might be tapered in some way, so it decreases from 1 to 0 the further away you are from the range. And then you give more weight to values that are close in the future than values that are further away. You sort of discount values that are too far away because things are going to change. You care more about what's going on in the short term. A little bit later, I'll talk about the value of a policy. So if D is my set of rules, the value of that set of rules is the expected reward or return, the expected value of whichever of these functions I'm interested in, y or u of y of t and so on, given the past. So that's locked. I know what ht it is. That's set in stone. I don't know what's going to happen in the future, other that I'm going to follow the rules, and I'm going to follow rules D. And if I do that, what's my expected reward? That's called the value of these rules D, of this policy. Okay, so what sort of methods are there out there? Well, there's a whole raft of them, okay? There are 2 major methods called Q-learning and A-learning, and then a variety of others which I won't talk about, but I will mention, if you want to look up, outcome-weighted learning, which is an important and more recent class, and classification-based methods which are related to that. Let's start with Q-learning and then briefly on to A-learning. Q-learning stands for quality learning. Q is for quality, and it's based on the quality function. Okay? And the quality function is the value, that's your expected reward, remember, if at time t I choose action or treatment little a. So Q, it's defined at time t, it's a function of the past, so it's Q of ht, everything you know already is locked. It depends upon what decision rules you are going to apply in the future, So there's a subscript D there as well that says over the future I'm going to follow these rules. But for time t, I might not follow the rules. I might choose action little a. And that's the expected value, the expected reward if you do that. Action A now, rules D in the future. Then the procedure for modeling and estimation in this is very, very much like dynamic programming. Basically, you start at the back and work forwards. So you start with the final time point. In the final time point, there aren't any future decisions. Okay, you're making the last decision, so there's no future D, there's no D subscript on that. I've assumed capital T is the final time point. You put a model on that, you put a regression model on that. Okay, what's my expected return at the final time point if I choose action little a, superscript T, that's the final decision, and knowing everything that I know in the past. And then once you've got the model, you find the best action. So which of these actions is going to optimize my reward? Then you step back to the penultimate time, t minus 1, and you model the value, what am I going to get in the future, given what I know so far, which is ht minus 1, that should be a superscript, no, that's right, ht minus 1. Given my decision at time t minus 1, so given a t minus 1, and given at the next time point, the final time point, I follow the optimal rules, because I've just derived what they are, I know what they are. I don't know what h capital T will be, because I've got the random variable s superscript t to be revealed yet, but I'm going to follow the rules. And then I find that expectation for all possible actions, and I choose the action that gives me the maximum reward. And I keep on working backwards like that. So let's go back to my simple example. How would Q-learning work in this special case? Okay, so that in fact is my regression model for my final y. So y, my final outcome, has expected value 3, plus 3 if I chose action 1 at time 1, minus 1 if it turned out to be state 2 at visit 2, minus 1 times the interaction of first action and second state, plus 5, 6, etc. Okay? And if you work that out, it's a trivial example. Those are the possible first actions, second states, and second actions. Remember, everybody had the same first state, and those are my final y's. And if you check the arithmetic, the coefficients add up to the terms in the y column there. Okay, so I'll start at the end and say, what should I do for A2? Well, it will depend upon the history. So if my history is 0, 0, A1 is 0, A2 is 0, then I expect to get 3 for y if I choose A2 is 0, and 8 for y if I choose A2 is 1, so obviously I'm going to choose A2 is 1. So my optimal second decision is 1 if my history is 0, 0. If my history is 0, 1, it's still 1, but I should expect to get a smaller reward, 7 instead of 8. If my history is 1, 0, the best action is 0, and I should expect 6, and so on. Okay, so now I know my best rules at time 2 for each possible history. There's only 4 histories in this case. Now what do I do at A1? Well, A1 occurs before S2. S2 is a random variable, so I've got to average over the distribution of S2, which may depend upon A1. So if you look there, the distribution of S2 does indeed depend upon A1. And if you work it out, if I choose A1 is 0, and then the optimal A2, I'll get y is 8 with probability 0.2, and y is 7 with probability 0.8, and that's an expected value of 7.2. If I choose A1 is 1, and I follow the optimal decision at time 2, I'll get a lower expectation, 5.4. Okay, so my optimal decision at time 1 is going to be A1 is 0. And so now I've got some rules. A1 is always going to be 0 for everyone, and then A2 will be 0, 1, depending upon what happens to S2. Right, I'm going to talk very, very briefly about something called A learning, and the A stands for advantage learning. This is based on contrasts. So instead of having a regression model for something you can see, which is Y, you model the difference between two expectations, which is a strange construction, but it works. So remember, Q dt of ht at is the expected reward given history ht, given that I follow rules d in the future, if I choose A at time t. And under A learning, we choose to contrast that with the expected reward if we choose perhaps a different treatment at time t. So I've called it AT ref there, a different treatment. And one special case of this is called a regret function, introduced to the stats literature by Susan Murphy in a paper read in this room in 2003, I think. And this regret function says, not what do you get, what do you lose by making a particular decision? What's your regret? The best possible regret is 0, losing nothing. And Susan Murphy's definition is that it's the difference between what you would get, given HT, that's always fixed, given that you follow the best possible rules in the future, and at time t. So the first term on the right-hand side says, follow the optimal rules in the future, and choose the best possible rule at time t. The difference between that and something very similar, optimal rules in the future, same history ht, but a function little a, sorry, a treatment little a at time t. Okay? And the regret is a function of the a that is chosen. If your a happens to be the best, the two terms on the right side will be equal and you will have 0 regret. We're aiming to maximize reward, so anything else, the term on the far right will be smaller than the first term and I'll have a positive regret. This is a strange creature. It's modeling expectations under policies that we don't know. The optimal rules, we don't know them. That's what we're trying to find. But it works, and there are methods to estimate this from the data. Just for completeness, I did this on the simple example. At time 1, there is no history, and the regret for choosing A1 to be 0 turns out to be 0. The regret for choosing A1 is 1, turns out to be 1.8. And again, I'll just go back to there. And that 1.8 is the difference between 5.4 and 7.2, I hope. Yeah? So by choosing A1 is 1 rather than 0, I should expect to lose 1.8 before I know S2. Once I know S2, the regret depends upon the history, and there are 4 histories in that example. I've only put 2 down here. If the history is 0, 0, and I choose A2 is 0, I'm going to lose 5. If you remember the numbers in the table, there was an 8 and there was a 3. And if I choose 1, I'll have no regret. Right. I said that there are methods to estimate the parameters of models for A learning and for Q learning and for other methods that you choose to put into place. They all are based on assumptions if you use observational data for estimation. If you've got experimental or trial data where you're in control, things are okay. If you're just relying on what you saw out in the real world, then you have to be a little bit careful. Okay, so we need to introduce potential outcomes, or sometimes known as counterfactuals. And these are on the slide in the simplest possible case where I've just got one decision time and a binary treatment. Some sort of outcome y, there are 2 potential outcomes for each individual, y of 0 and y of 1. And these are the hypothetical values of y you would get if you chose 0 for that person or if you chose 1 for that person. They're not the conditional values, they're not y given that you've chosen 0, they're the hypothetical in this counterfactual world where somebody might have treatment A, might have treatment B. And then you can use these to construct things like the average treatment effect. This is the average in a sample of what everybody would have got if everybody had been given 1, compared to the average that would have happened if everybody had been given 0. Okay? Of course, that doesn't happen. Some people get 1, some people get 0. And that's the fundamental problem of causal inference, that only one of the potential outcomes can ever be observed. So we associate with each individual a whole raft of what might have happened if, but only one actually does happen. And that's the one that corresponds to the selected A. Okay, so to make progress, we need to make assumptions, and the assumptions we need to make here, at least some of them, are always untestable. You can never tell that these assumptions are perfectly correct. I'm getting a 5-minute warning, but I know that. Okay, and so there's a quote there. Okay, so here are three, the first of 3 assumptions that are in this evening's paper. The first one is sometimes called ignorability, sometimes known measure confounders. What you might have got if action 1 was chosen, what you might have got if action 0 was chosen, are independent of what was actually chosen. Right? That's a bit circular, but it's saying that the counterfactuals do not depend upon the actual treatment assignment. And there's a version of that for if you've got longitudinal sequences as well, called sequential ignorability. So at every time point, the actual treatment assignment doesn't affect what might have happened if you'd had the other treatment assignment. That's A1 in this evening's paper. I am going to overrun slightly, I hope that's okay. So back to the warfarin data, the plots that I showed 15 minutes ago were based on some hospital notes that I was given, and I typed 9,000 warfarin results into a computer myself over parts of February. And along the way, I saw some written notes alongside the numbers. And here are 2 quotes that caught my eye. So one of them, in the middle bullet point, this patient has bad sight. They may have been taking 3 milligrams instead of 2 milligrams, request large print. Okay. So following that, you could see in the data that the INR went back into range, but the treatment didn't change. Okay. So if I hadn't seen that quote, I would have thought this patient's INR, blood clotting speed, had just gone back to normal on its own. Nothing to do with treatment. But in fact, he went back to normal because something else happened that wasn't the treatment. They got bigger print. The second one, nursing home has been giving patient 1 to 2 glasses of cranberry juice every day, exclamation mark, exclamation mark. The person who wrote that, unlike me, knew that cranberry interacts with warfarin. So they told these are all elderly patients, the home about the effects of cranberry, and they stopped. Okay? These are confounders. These are things that affect the outcome, but are not the treatment. In those 2 cases, they are measured confounders, that we saw what, we have notes on it. More often, there will be unmeasured confounders, things like this that are not in the notes. And we can't have those. We have to assume there are no unmeasured confounders if we're going to draw valid causal inference. We have to assume that the reason for a treatment change is known to us when we analyze the data. Then we have an assumption of consistency. So this one is, it seems fairly obvious, but it's always written down. I said there are 2 potential outcomes, Y1 and Y0. There's one actual treatment, and the consistency assumption is that the potential outcome corresponding to 1 is the actual outcome if the treatment was 1. And the same for 0. And that's assumption A2 in the paper this evening. And then for estimation purposes, often a positivity assumption is required, and that means every possible treatment happens in the data, so we can see what's going on. We can't possibly estimate the effects of treatments that don't occur in the data, at least without other assumptions. You might want to assume a parametric model, but not without some form of assumption. So those are the three assumptions that are in the paper tonight. There's one other assumption and another scenario that are not in the paper tonight that I'm going to mention, and then Eric Lheure is going to tear them apart. And not a helpful phrase, but the first is called the stable unit treatment value assumption, SUTVA. And this is that the potential outcomes for any unit don't vary with the treatments assigned to other units. So what I might have got if I was given treatment A1 doesn't depend upon what treatment is given to Paul. What I might have got if I was given A0 doesn't depend upon what treatment is given to Eric, and so on. And there's no different forms of treatment level that we don't know about either. So treatment is either 1 or 0. There isn't a 1.5 or a 1.2 that is not known to us. The other one that is not really assumption for causal inference, but which is usually a requirement for estimation and inference, is that we have data on IID people. So we've got a sample from which we can estimate. Okay, I've overrun. I apologize for that. I'm going to pass on now to Professor Lheure.
Well, thanks all for coming, and thank you to Robin for being willing to do that. I really appreciate it. I also want to acknowledge that Nick Meyer, that Nick Meyer is here sitting in the back, and he's the student who did all this work. I've never done a demo before, and so I thought what might be useful would be to pick off all the things I thought were unusual in statistics and talk about those. So there's a lot of stuff in this paper that isn't seen sort of in typical statistics training, and so I thought I would cover those things, and then that might make the main message of the paper tonight easier to follow. So here's a roadmap. I thought I'd talk about online decision problems. So these are decision problems that you're making as data are accruing. So what we just saw, you could imagine collecting data on a batch of patients and then doing Q-learning or A-learning to estimate an optimal strategy. In online learning, we're trying to make decisions as we go, and that ends up requiring different kinds of algorithms. Then I'll talk about Markov decision processes. These are the most common framework used to model decision problems that are ongoing, either with long or indefinite time horizons. And then briefly talk about spatial temporal decision making. And just as a warning, there's a couple of repeat slides that are here and tonight, but I thought that would maybe be helpful to set the notation for tonight. So this is a schematic for an online decision problem, and thanks to Rob, we have, I think, pretty good overlap in terms of the notation. So you start off by observing a state I'll call S1, then you choose an action or a treatment or an intervention, A1, then you transition into a state S2, and then a function of those three things, the state you started in, the action you chose, and the state that you transitioned into, is used to determine an outcome. So the outcome may just be a subset of S2, or it may account for where you got to. So maybe you look at change in say, weight gain, for example, where you started and where you ended up. So it's a function of S1 and S2. Or maybe it's a function of where you started, where you ended up, and how much the treatment costs. So it's a function of all three, but that's the idea. And so here, ST is the state at time t. A is this action. And I bolded A here because sometimes that action is going to be a vector, and sometimes it'll be a scalar. And so I've tried to be consistent and make it a vector when I'm talking in general. And then Y is an outcome, which also may be a vector. So that may be several measures of side effects or efficacy, or in our case, it's going to be outcomes at a bunch of different locations. Okay, so a deterministic strategy, which I'll call E, is a map from the domain of the state to the set of actions, so that under E, you select action E of ST if you observed state ST. Okay. So in an ideal world, what you'd like to do is if we define the marginal utility, this is in the previous part, V of E, to be the expectation if you were making decisions according to E of the sum of the utility. So that's expectation of the sum from t greater than 1, ut of yt, where ut is some utility function that measures the goodness of yt. And it's also defined in such a way that that expectation is finite. So you saw in the previous example, one where you put an exponential discounting factor that was decaying or dividing by t and then taking a limit. Those would be two options for this utility, but obviously you want that infinite sum to have a finite expectation, so that's implicit in the utility. And the optimal strategy maximizes that. So the ideal setting is shown here. For every candidate policy E, what you'd like to do is you'd like to just evaluate it. So you start off in S1, you apply E to get A1, you go to S2, you apply E to go to A2, and so on. And then you could just take an average or apply the utility and take an average utility, and that would give you an unbiased estimator of the value of a strategy E. You would do that for all the E's, and then pick the best one. Okay? Of course, the problem is that we can't do that. We have to learn as we go. So what you do is you have to somehow choose which E you're going to follow at every time point, and the hope is that eventually you get closer to the optimum. So this is a schematic for kind of what we're stuck doing. So early on at S1, you might not know very much about the system, and you also have hardly any data. But you'd like to use some combination of theory and the data you do have, which in this case would just be S1, to choose a policy or a rule I'll call E hat 1, because it has the data, so I put a hat on it. You go to, that gives you A1, you go to S2, now you have a little bit more data, and you still use theory, and you choose a rule E hat 2, and so on. And the idea here is that time marches on, you'd like to rely more and more on data and less on theory. Okay, so here's a warm-up problem. This is kind of the simplest online decision problem that matches the kind of things that we want to do. And this is called a contextual bandit. So this is a common problem in computer science. It shows up in adaptive clinical trials in the stats literature. So suppose you have a stream of patients. They're arriving one by one. And when the patient arrives, you measure their covariates. You assign them a treatment. You observe their outcome. And then the next patient arrives. Okay, so the idea is you get to use the results of all the previous patients to decide what to do for the next patient. So again, ST would be patient covariates. We'll assume that we just have a binary treatment, so 0 or 1. And YT is the outcome, and it's a scalar, and it's coded so that higher is better. So here the utility is just the identity function. Okay, and a treatment strategy in this context, E would be a map from the space of covariates to the space of actions, so from RP is 0, 1. And just as in Rob's talk, we'll define QSA to be the expectation of Y given the state and action, so that E opt is the argmax of the Q function. So the crucial thing here is that these patients are IID. They don't depend on each other. So they're coming one after the other, but they comprise an IID sample. Okay? So there's no dependence over time among the patients. And so the optimal thing to do is just to give them the treatment that maximizes their expectation. Okay? So the natural idea, given this expression for E opt as the argmax of the Q function, is to first construct an estimator, say Q hat of Q, and then you take your estimator to be E hat to be the argmax of the estimated Q function. And the nice thing about this formulation is that, well, the Q function is a regression, and we know how to estimate regressions. Okay. So the sort of usual RCT approach, which I call a batch approach, would be go collect data on the first capital T patients. So you get a batch of patients. Each patient that comes in, you flip a coin and assign them a treatment at random. After you have T patients, you estimate that Q function with a regression. So you regress Y on S and A. Okay, so you could use a linear model as I've shown here. So QSA beta would be S0 transpose beta 0 plus A times S1 transpose beta 1, where S0 and S1 are features of S. And then you could fit your model. Beta hat is the least squares estimator, so the argmin over the sum from T equals 1 to T of YT minus QSA beta squared. And then your estimated rule would be E hat capital T of S is the maximizer of your estimated Q function. So you take your linear model, you plug in your coefficients, and that's it. Okay. So this would be kind of the standard batch approach, meaning you do a batch of patients at once. So if we do this, and then we treat patients like this ever after. So we do this once from a clinical trial, and we think about all the future patients we see, and if we're N patients into that, where N is bigger than T, then the cumulative difference between outcomes assigned under E hat and the optimal is big O of capital N, meaning it's growing linearly with patients. Okay? So you're making, on average, a little bit of a mistake with every patient. Okay? It never goes to 0. And you can convince yourself this is true by first thinking about, well, the first T patients, clearly half of them got the wrong treatment for them. You just flipped a coin. And then thereafter, you just think about, there's a small chance you got this wrong if your estimate. So for every patient, for every S, there's a small chance that your Q hat gives you the wrong answer. So that's not negligible. And then that error never goes away because you've never updated your estimator. Okay? So the natural question to ask is, well, can you do better? And I should also say that you can point this out. You might say, well, why don't you just keep fitting the regression model as more and more data accumulate? You can show that that too will have linear regret, even though it's more complicated to sort of show. Okay, so it turns out that doesn't save you. Okay, so that brings us to Thompson sampling. So this is an old idea, and it's an intuitive idea. So the patients come in, and when the new patient comes in, you have two choices, treatment 0 and treatment 1. And you assign them treatment 0 with the posterior probability that treatment 0 is optimal for that patient, and you assign them treatment 1 with the posterior probability that treatment 1 is optimal for the patient. And then once you observe their outcomes, you update your posterior, and you just keep doing that forever. Okay, so that's the idea. So you have to posit a model for the conditional distribution of y, given S and A. So notice there's more modeling here. So for example, just to match what we did on the previous slide, let's put a linear model plus with a Gaussian error. And you have to then specify a prior over beta, and also the variance, sigma. So you specify that prior. And then at time t, we'll draw AT from the posterior of argmax over A of QSA beta. So the posterior is really over beta, right? And you have S, but you draw a beta, and then you take the argmax, and that gives you A. So if you do this, you can show that after treating n subjects, the cumulative difference between outcomes under E hat n and E opt will be big O of square root n log n, which is much smaller than big O of n. Okay? It turns out, though, that it took a long time to figure this out. So 1933 was when this was first proposed, and if you look at the papers referenced in the footnote, these proofs came out in 2012, 2013, were for very special cases. More general results came out a little bit later, for linear model case with normal errors. And so it turns out to be non-trivial to show this, but you do get much better regret. And you can also show that you can't really do better than this. So it's optimal. Okay, and if you think about dividing everything by n, if you take an average regret, going into the future, you'll see this goes to 0, where of course something that's big O of n will not. Okay, so that's Thompson sampling for this case, and then I want to get to it for the more complicated case, which is in the decision processes. But please stop me if there's any questions as we're going. Okay. Okay, just some final notes on this before going to the MDP case. We need to be able to balance action selection with model, and that improves our model with those decisions that look good based on our estimates. So if we think about Thompson sampling versus random sampling, so we need to randomize in order to continually improve our model, but we'd like to do it in such a way that we're randomizing with less and less probabilities. We get more and more evidence for what the right thing is to do. Okay? And this is the whole mantra of adaptive clinical trials. This is what they're trying to do, and you see these bandit-type algorithms there. In computer science, this is known as the exploration-exploitation trade-off. Not surprisingly, the term exploitation didn't catch on in medical decision-making, so that's not used. They sometimes say ethics-efficiency trade-off instead, sort of what's best for the patient now versus future patients. Thompson sampling is an intuitive heuristic. It has this Bayesian framework, and so what's nice about that is when you think about complicated settings where you have maybe missing data or noisy measurements, you can incorporate all of that sort of seamlessly. And so even though I'm not a Bayesian, it seemed like a right place to start. And that, of course, is helpful when you're talking about infectious disease management, where you're talking about spatial temporal problems where everything is dependent. And also you might have partial measurements, you might have convenience sampling, and so on. The frequentist operating characteristics aren't fully understood, but they're now kind of a current area of focus in CS, as you saw in the previous slide. Okay, so on to Markov decision processes, or MDPs. So this is a standard model for sequential decision problems. So this is almost universally used in the reinforcement literature in computer science. And what it means is, well, it's Markov. So that means a state at time t+1 is independent of previous states and actions given the current state and action. Okay? It's also homogeneous, meaning that the distribution of the state at time t+1 given the previous state and action doesn't change over time. And finally, we'll assume that the outcome is a function of next state, action, and previous state. Okay? And that's typical. If that didn't hold, however you define state, you could extend state to just include whatever it is you were calling the outcome. Presumably, you can measure the outcome, so this isn't really an assumption. Something that I think comes up is that any decision process can really be cast as Markov and homogeneous. So in that sense, sometimes people like to think that this isn't a strong assumption. And the way that you can convince yourself that's true is Well, if it wasn't Markov, I can just redefine the state to go all the way back to the beginning. And if I call that my state, then of course that's not succinct at all, a summary of the past that's sufficient for making a decision now. And if it wasn't homogeneous, well, you could redefine the state by concatenating the current time. And of course, no two states will have that same first index, and so mathematically, of course, it's homogeneous. But this is not useful from a decision-making point of view, right? Because if you define the state as everything that's happened till now, there's no way to extrapolate for future decisions. And if you do this trick of concatenating the state with the current time, well, again, there's no way to extrapolate, so it doesn't really buy you anything. So mathematically, yes, everything is homogeneous in Markov, but the reality is you need to define the state very carefully to be a succinct summary of the past, and that's a non-trivial thing to do. And usually that requires interaction with domain experts and so on. Okay. So here the objective, just as a reminder, VE is the expectation if you were making decisions under E. And I'll express all this in terms of potential outcomes tonight, but I just thought I would kind of do this hand-wavy bit here. In the Markov decision process, it's completely determined by that transition probability. So if you knew the distribution of the current state given the previous state in action, everything else is determined. The entire system is determined, so you just need to know that. And so a natural batch approach would be to first assign treatments for T time points according to some exploration policy or exploration distribution. So you can think about that as uniform, but it could be something else. It's just the point is it's known, and its support is on all possible actions at all possible time points. Okay? Then you posit some kind of model for that transition, right, for the distribution of ST plus 1 given ST and AT. So you have a parametric model for that, indexed by beta, and then you construct an estimator, beta hat T of beta, and then once you have that, you know everything. Once you have that transition kernel, you can then back out what V must be, right? So you get V hat, and then you construct E hat to be the argmax over some class of deterministic maps of V hat T. Okay? So the idea again, go for T time points, get a batch of data, estimate the transition kernel, and then just use that to make decisions as a plug-in estimator. Is that clear? But you can show that this has the same problems we saw with the contextual bandit. I won't go through the arguments, but again, it's going to have this linear regret. And as long as you can convince yourself that you could be wrong at time capital T with some small probability and you use it forever, well, then that's where you get your linear regret. It also has this undesirable property of having to follow this exploration policy early. So if you're talking about trying to control an infectious disease and you're randomly assigning treatments, the disease can really spread out of control early, right? And of course, it also might not be ethical to do that. And so it's going to be really important when we talk about infectious disease management. Thompson sampling, on the other hand, would look like this. So you posit a model, again, for the distribution of the next state given previous state in allocation, indexed by beta. You specify some prior over beta. And then at every time t, you draw beta from the posterior, or say beta tilde from the posterior. You compute E tilde to be the argmax over your class of the value function you get if that were the true parameter value. And then you set A to be E tilde of S. And then you just keep doing that. Okay? So notice this three-step process makes AT a draw from the posterior of the argmax over the set of deterministic policies of V beta. And I put that subscript beta just to emphasize that V is completely determined by beta, because it's completely determined by the conditional distribution, which is determined by beta. Okay? And you can show that you get sublinear regret, and I will show that tonight. So there's a teaser, I guess, or something. Okay. So in this context, Thompson sampling is a very general class of methods. You saw that it was just some transition kernel. It applies to any MDP. It allows you to incorporate scientific theory. This is important in disease modeling where they give a lot of thought to what those transition kernels look like. The decisions reflect the evidence supporting each action choice. Right? This idea of having, well, what's the posterior probability that that's the right thing to do? That's the probability with which you select an action. You can handle spatial temporal structure, missing data, and so on. Of course, the flip side of incorporating the scientific theory into a parametric model is that that model could be wrong, or probably is wrong, so you can get bias. It's computationally intensive, so that draw that's here, draw AT, that could involve MCMC and stochastic optimization at the same time, which of course is very complicated and messy. And you can show that in some cases you can have either under or over exploration, meaning that you would do better to explore less than Thompson sampling does, or better to explore more than Thompson sampling does. So it's easier to construct examples where in finite samples that happens, even if it gives you an optimal rate. The finite sample behavior can still be poor. Okay. And then finally, I just want to talk about the spatial temporal problems. This is the kind of problem we'll consider tonight. This is one of the repeat slides, so I thought I'd review what white nose is. So this is a fungus that's killing bats in North America. Interestingly, it's here in Europe, but actually isn't nearly as devastating. So here are some headlines. Fungus that's killing bats isn't going away. This one I put up here just because I really like the term bataclysm. So the secret bataclysm, white nose syndrome and extinction, relentless bat plague not abating. And if you go to Google News and search for white nose syndrome bats, you'll see a bunch of headlines from this week about how it's still killing millions of bats. And so it's really having a big impact on agriculture and on ecological stability. And there are some of these species it's 90% fatal and they're endangered, so there's a lot of concern about what will happen. And so the disease, in a nutshell, is it's a fungus that grows on bats when they're hibernating. So this, keep wanting to point with this. So on the lower left, there's a bat hanging upside down, so its feet are at the top, and its nose is on the bottom, and you can see this white on its nose. That's this fungus. This fungus is white. It gets on them. When they're hibernating, they don't move, so it grows sort of unchecked, and then it destroys the membranes in their wings. It can also wake them up, and they fly around, and that burns fuel cell, or burns up their restored energy, and they die. And so the original question was, where should we apply interventions to stop the spread of the disease? And one of those interventions is shown in the middle panel. That's an artificial cave. And the idea there is that if you put an artificial cave up, you can go and clean it out. So you can go get the fungus out of there, where you can't go into a cave and spray fungicide everywhere. The only problem is that they're very expensive. Okay? So putting them everywhere would be effective, but it's not feasible. So you want to be very careful about where you place them in space. And just as a bit of trivia on the right, that's a poster for advertising that Chevy takes byproducts from their Corvettes and puts them in these artificial caves. So I found that out while getting my oil changed. So here's the problem. There's the United States, and the outlined regions are counties. And the spread of the disease is color-coded. I know that the color is a little distorted, but it starts up there in red. That's Lheure County, New York, and it spreads through the Northeast and then across. And so each of those little counties has bats that are susceptible to the disease. And the question was, if we measure something in each of these counties and we measure the epidemic, if at every year you could put down a small number of these artificial caves or some other intervention, go forward a year, measure how well it performed, and then possibly move the locations, how should you best do that to control the spread of the disease over a long time horizon? Okay? So what you want is you want a map from all the available information, including epidemic sort of evolution and features of each of these counties, and you want to output a subset of locations to treat. Okay, so we'll call that an allocation strategy. And there's about 1,100 counties, and if you treat a small subset, the number of options is very big, and that's going to be important later. Okay, so the goal here was to control the geographic footprint of the disease. Impacts, I mentioned ecosystem diversity, these spread of human disease in terms of disease vectors like mosquitoes. Agricultural pest control, so it turns out to be very expensive, so it's worth tens of billions of dollars because these things eat insects, and for the insects they don't eat, you have to spray pesticides, which are both expensive and also damaging. And in terms of interventions, there's chemical and biocontrols. There's some work in vaccines recently that wasn't available at the time this paper was written, artificial caves and cave closings. And then again, this goal is to estimate a map. I thought I would mention one other project that's not in the paper but has a similar kind of feel, which is conservation of Puerto Rico. 2013, Puerto Rico, the Department of Natural and Environmental Resources and U.S. Fish and Wildlife Service committed to increase the amount of conservation area. And so here, the idea was that there's all these little parcels of land, and you want to change some of them. You want to pick the real key parcels to change to increase the landscape for certain kinds of animals, so frogs and birds and pollinators in particular. And so the focus was on this region called the Bosque Modello, and the question was, which parcels of the land should you pick over a sequence of 5 years? Okay, so here's the region, it's down here. And so originally they wanted to do the whole island, and we convinced them to do a smaller region because it was hard enough as it was. So there, again, the goal was to maximize habitat for birds, frogs, and bees or pollinators. And long-term environmental impacts is we're only going to do this once. they're not going to do this again. It's very expensive. Coffee plantations were a key point of intervention, and that's a key part of their economy. And then also, this was supposed to be used as a template for adaptive conservation, and so the pressure there was that if we screw this up, we can then subsequently screw up a lot of other projects that would use this as a template. So we felt very nervous about that. In terms of interventions, here you can incentivize landowners to improve habitat quality. For example, convert sun-grown coffee plantations to shade-grown, increase management efforts on protected land, or you can actually just buy land and protect it. And here, the strategy would be a map from measures of landscape value and the results of a cadastral survey to a subset of regions, and again, doing that every year. Okay, and there are lots of problems that look like this, as you can imagine. Anything that has a spatial temporal component, the obvious one is the spread of disease on a network. So you have a network of individuals, and the disease is spreading across the network. Ecological management, like in Puerto Rico, we've also done this for managing catch sizes. So how many hunting licenses should you give for mallards, for example, and others. Okay, so the thing that's, and this is the other slide that's going to be a repeat, but the reason that this is so difficult is for things like the Puerto Rico problem or the white nose problem, you don't know how well these interventions are going to work when you start. So you really need to make sure that you're going to be able to estimate treatment effects early so you can exploit them later to make better decisions. You have noisy, incomplete, sparse measurements. People are going out to these caves and looking around to see if the fungus is there, so there's obvious measurement error, there's convenient sampling. They don't take the samples all at the same time every year. It's high dimensional, so in white nose, there's 11,000 measurements per time point. Here, this is an online problem which we've been talking about, so you're changing the distribution over which you select allocations at every time point. And what that means is that the sampling distributions are very complicated, so doing inference is complicated. In terms of computation, if you can do something or not do something at every location and you have 1,000 locations, it's a very large number of choices, and that's just for one time point, and you're trying to do this for many steps into the future. And so you can't enumerate the choices in white nose syndrome even with all the supercomputers in the world running for a lifetime. Okay, so just to review the notation that we'll be using tonight, so it's again a sequential decision problem. It's going to have allocations, which will number 1 through capital L. So those could be the counties in white nose syndrome, they could be the parcels of land in the Puerto Rico problem, they could be nodes in a social network if you're talking about an infectious disease, and so on. And we'll talk about discrete time, so these are, it's evolving at, say, time points 1, 2, 3, and so on. In white nose, these are years. In other problems, they could be event-driven. So there's something that prompts you to need to make a change. So you can imagine that, in something like the warfarin example, maybe they go out of range and you need to do something. Every time t in every location L, you observe a state, which I'll call SLT. You observe an outcome, which I'll call YLT. You select an allocation, ALT, which is going to be 0 or 1. 0 means do nothing, 1 means do something. And then we'll leave a subscript off to denote the union over all locations. So ST would be the set of all states at all the locations at time t. AT would be a vector of length capital L of 0s and 1s, coding which locations got treatment, which ones didn't. And then YT would be a vector of length L of outcomes, okay, across all the locations at time t. And so this should match our notation from before. And we're going to assume that an allocation is based on the state ST at time t. And what you're really assuming there is that you've done a good job defining the state to capture everything that's happened up until now. So you've come up with a good summary. Okay, and again, that's a non-trivial problem. Okay, we're going to assume that it's Markov. So that means we need a density for the outcome given the state and allocation, and for the state given the previous state and allocation. And we'll assume that those are indexed by beta and theta. Now, this is how we did it in the paper, which is why I kept it this way. It can be done more succinctly by just making the outcome a function of the states and talking only about the state, but just to match the paper, this is how we did it there, because we thought it was a little more clear in that context. So you have these two densities, you have two parameters, beta and theta. To match earlier, you just sort of put them together. And now we can just do Thompson sampling. So even though it's a spatial temporal domain, it's very high dimensional, we can still do Thompson sampling, and we'll do it as follows. First, we construct estimators beta hat and theta hat. So that could be a posterior mode. It could also be a maximum likelihood estimator, which we're going to do as a surrogate for a posterior mode, right? And then we're going to draw beta tilde and theta tilde from the sampling distribution of the maximum likelihood estimator as a surrogate for a draw from a posterior. Again, because these really high dimensional spatial temporal problems, it's very hard to do MCMC. It's very expensive. And so this is, again, a sort of cheap surrogate to get a draw from the posterior. Then you simulate the process under beta tilde and theta tilde to form an estimator V hat of V, just like we did before. And then you use stochastic programming to compute E hat to be the argmax of that estimated marginal mean outcome over all the deterministic strategies. Okay, so that's the whole idea. And here's the picture. Am I going? I feel like I might be going over time. Am I over time? Okay. All right. I only have one slide left. So here it is, sort of as a process. You observe a state. You do maximum likelihood. That gives you beta hat and theta hat. You draw from a sampling distribution, again mimicking a draw from a posterior. You do simulation optimization to get E hat. Set A to be E hat. Go forward a time step. Observe the next state. And this just goes round and round. Okay. So that's the whole idea. So it's just like the bandit problem, only now in this sort of MDP setting. And then what are we going to talk about tonight that's different from here? So that was, hopefully, that'll give you the key idea for tonight. And then we're going to talk about formalizing the causal inference part. So establishing formally what we mean by an optimal regime, using potential outcomes, dealing with spillover effects, meaning if you apply treatment in one location, it affects the outcomes at other locations. We'll go over an interpretable class of strategies delta, which was here is kind of presented abstractly, but I'll give you a concrete class. I will give you a couple of theoretical properties of Thompson sampling in these spatial temporal problems. So that's a little bit off script in terms of the paper, but I was going to give you the rates of convergence and some finite sample concentration inequalities. And then also demonstrate this with some simulation examples, both on networks and on the white nose problem.